The James Webb Space Telescope, JWST, has been in the news since its launch on Christmas Day 2021. Since then, the superstar telescope has opened up the universe in ways no one expected. He recently discovered 6 galaxies that existed only 500 million years after the Big Bang. These galaxies are well-formed and contain more stars than modern galaxies like our Milky Way. These galaxies should not exist because they challenge our model of cosmology. Researchers at the University of Minnesota have discovered that one of these galaxies is so strange that we may have to go back to the drawing board. JWST represents a major advance in our ability to explore space with its advanced instruments and unparalleled sensitivity. JWST promises to change our understanding of the universe, especially in the field of early universe studies. One of JWST's most remarkable features is its ability to gather about 10 times more light than its predecessor, the Hubble Space Telescope. This significant increase in light-gathering power will allow JWST to peer deeper into space, revealing celestial phenomena previously unobservable. By capturing abundant photons from distant galaxies and cosmic structures, JWST opens a new window of research, providing astronomers with unprecedented insights into the origin and evolution of the universe. JWST's enhanced sensitivity in the redder and longer wavelengths of the infrared spectrum gives astronomers a unique tool for studying the early universe. Unlike visible light, which is often obscured by cosmic dust and gas, infrared radiation can penetrate these dense clouds and reveal hidden celestial treasures that would otherwise remain invisible. This property is especially valuable for observing distant galaxies and ancient stars whose light has been extended to longer wavelengths by the expansion of the universe. Using the power of infrared astronomy, JWST allows scientists to look back in time to the cosmic dawn, the era when the first stars and galaxies emerged from the primordial soup of the early universe. This cosmic dawn holds the key to unlocking the fundamental mysteries of the formative years of the universe, including the processes of galaxy formation, star formation, and cosmic reionization. One of JWST's main goals is to study the reionization epoch, a key stage in the history of the universe when intense ultraviolet radiation from early stars and galaxies ionizes neutral hydrogen gas. By observing distant galaxies and quasars during this epoch, JWST can illuminate the timing, extent, and mechanisms of cosmic reionization, providing important insights into the transition from the cosmic dark ages to the bright universe we observe today. JWST's infrared capabilities allow it to peer through the veil of cosmic dust and gas, revealing the hidden processes of star formation and galaxy evolution. By probing the infrared emission from dusty star-forming regions and protogalactic disks, astronomers can trace the formation of stars and the assembly of galaxies over cosmic time. Revealing the complex tapestry of cosmic evolution, JWST promises to change our understanding of exoplanets, worlds orbiting distant stars outside our solar system. By detecting weak infrared signals from the atmospheres of exoplanets, JWST can analyze their composition, temperature, and potential habitability, paving the way for the search for life beyond Earth. JWST's scientific potential is broad and varied, spanning a wide range of astronomical disciplines, from the study of distant galaxies and quasars to the study of nearby exoplanets and planetary systems. Its unprecedented sensitivity, combined with its infrared observing capabilities, places JWST at the forefront of modern astronomy, poised to reveal new insights into the nature of the universe and our place in it. As astronomers prepare to begin a new era of discovery with JWST, they stand on the threshold of a profound journey that promises to illuminate the darkest corners of space and reveal the mysteries of the origins of the universe. To understand the early universe, we must go back to a point where time and space did not exist. According to the theory of cosmic inflation, the universe was born with the Big Bang, an unimaginably hot and dense point. When the universe was only 1/100th of a billionth of a second old, it experienced an incredible burst of expansion called inflation. During that time, the universe first doubled in size at least 90 times, going from subatomic size to golf ball size almost instantly. After that, the universe continued to grow, but more slowly. As space expanded, the universe cooled and matter formed. Just 1 second after the Big Bang, the universe was full of neutrons, protons, electrons, positrons, photons, and neutrinos. For the first 380,000 years, the universe was almost too hot for light to shine. However, 380,000 years later, matter began to cool enough to form atoms. After this point, the universe was plunged into darkness, as stars and other luminous objects had not yet formed. Fast forward to 400 million years after the Big Bang, and we see the universe beginning to emerge from its dark ages. This period of the evolution of the universe is called the reionization period. During this phase, which lasted more than 500 million years, the first stars began to appear and the formation of galaxies began in the first billion years after the Big Bang. Galaxies are entering their teens. However, the James Webb Space Telescope found not one, but 6 galaxies that fully formed only 500 million years after the Big Bang, and that's a problem. Using the first observations from the James Webb Space Telescope, a team from the University of Minnesota looked back more than 13 billion years to find a unique small galaxy that gave birth to new stars very quickly. Its size. The galaxy is one of the smallest ever found at this distance and could help astronomers learn more about galaxies that existed shortly after the universe began. The galaxy is about a millionth the size of the Milky Way, but it still forms the same number of stars every year. The galaxies that existed in the infancy of the universe are very different from what we see in the nearby universe today. Scientists studying these galaxies could help us figure out how and when these first stars and galaxies were born from the dark ages of the universe. How the universe came into being is still a mystery. Over the days, observations made by JWST show that the universe, especially in its early stages, was stranger than we imagined. JWST not only discovered these early galaxies, it also discovered a black hole that is almost as old as the universe. Scientists have discovered the oldest known black hole in the universe thanks to powerful sensors that caught the elusive creature. Dwarfing our Sun by 10 million times, this supermassive black hole was at the center of the galaxy 570 million years after the beginning of the universe. The time is so far away that it is difficult to understand. For perspective, the universe is estimated to be 13.7 billion years old. Observations collected by the James Webb Space Telescope have revealed an active supermassive black hole with a mass 10 million times that of the Sun.
It is actively growing, gathering matter from the surrounding space only 570 million years after the Big Bang. It is the earliest discovered growing supermassive black hole, although scientists hope it would not hold the record for long. The black hole was found in one of the earliest observed galaxies, previously known as EGSY 8, but later renamed CN19. Its discovery could help solve one of the biggest head-scratchers of the early universe: how cosmic dawn black holes grew so large in such a short time. The claim, "We have found the most distant active galactic nucleus, AGN, and the most distant, earliest black hole we have ever discovered," represents a huge advance in our understanding of the cosmos. This marks the discovery of the CN19 galaxy, which contains not only an active AGN, but also an extraordinary ancient black hole. That discovery is a testament to the remarkable capabilities of modern astronomical instruments and scientists' continued pursuit of knowledge. The journey to find CN19 began with a careful study of the universe's infancy. Armed with cutting-edge technology and a deep curiosity about the early cosmos, scientists began to study star formation in its early stages. Their target was CN19, a celestial being shrouded in the mists of time but shining with the promise of uncovering the secrets that lie in the shadows of the cosmic dawn. Star formation, a fundamental process in galaxy evolution, emits a characteristic signal called Lyman alpha emission. This feature, which results from the ionization of neutral hydrogen in rising stars, acts as a beacon that illuminates the darkness of the early universe and entices astronomers to probe deeper to unravel the mysteries of cosmic birth. When scientists turned their eyes to CN19, they had a revelation that exceeded their wildest expectations. Amidst the faint whisper of star formation, a new voice emerged. The AGN, stirring after eons of slumber to cast its fiery gaze into space. This discovery defied conventional wisdom, challenging our understanding of the dynamics of the early universe and raising profound questions about the interaction between black holes and galaxy evolution. The coexistence of an AGN and a black hole in CN19 provided a fascinating glimpse into the cosmic drama of the ancient ages of the universe. It suggested a complex interaction of forces, the birth and death of stars, the collapse of gravity, and the inevitable march of time, forming the celestial landscape into a crucible of cosmic evolution. The significance of this discovery reverberated through the scientific community and sparked a frenzy of research and speculation. As astrophysicists, armed with new knowledge and unbridled curiosity, set out to search for the secrets hidden within CN19's luminous embrace.